All right, welcome back. Now we're going to look at how we are going to apply the integrating factors that we have derived in the previous lesson. Right? Okay. Now, just to recap on the integrating factor that we have derived, the formula for the integrating factor is given as exponential. Okay. Right. Now, this is the formula that we use to obtain the integrating factors for the first order ordinary differential equation. Okay, but anyway, before we can actually use this integrating factor formula, we have to make sure we can obtain, for instance, in this example here, we are given this first order ordinary differential equations. Okay, I'm going to write this one down. Okay, in this approach here, we are going to use a more trimmed down version of the original methods of integrating factors. Right? So here we try to omit the proof how we actually obtain the integrating factor. Instead, we're going to use the integrating factors directly in solving this first order ordinary differential equation. Now, before you can do that, you must make sure that the coefficients of dy dx must be equal to a 1. So in order to do that, we have to divide the whole equations by x to obtain this form. Okay, so first step, you make sure the coefficient for dy dx is a 1. And then next, the coefficients for y must be a function of x. If this is a mixture of function of x uh, and y that you can separate, is still fine. If it is a mixture of function of x and y together that you can't separate, then we can't apply this integrating factor method, right? Okay, now once you're ready with this, since the integrating factor is given by this, and then your final form of solving is always given by d I y equal to I g here, where the g actually refer to this section. This part is a function of g. This is the function of g, right? Whereby the functions of f itself, where the function of f is given by 1 minus 2x over x here. Or you can simply write as 1 over x minus a 2. Right. So I hope that is clear. So our first step, once we have set up all this, once we have obtained this structure, okay, once we have identified our fx, now it's time for us to obtain the integrating factor. So integrating factor is the exponential of the integrations of the functions f. Now I'm going to write a different form here. So exponential integrating the functions of f. Okay, so this is how it look like. Now first step is we're going to integrate this. Okay, so by integrating this, we will have, okay, we will have a ln x minus 2x. That's what we have, right? So from here we can further simplify it if we can, right? That is simply ln x minus 2x. We can actually simplify as ln x like this multiplied by e negative 2x. And then we know that exponential ln x is basically just x. Therefore, there you have it. That will be our integrating factor. Okay. Now, once you have obtained the integrating factor, then we're going to refer to this section here, where we're going to solve the first order ordinary differential for this question here. Right. Now let's try to solve this. Our second step will be we're going to rewrite this as dx. We have obtained our I, which is this. And then we also have an I on the other side. Multiplied by g, which is a 1. Okay, so those are the one that we have. And then, of course, we're going to rewrite in this case. And then we're going to perform the antiderivative. All right, in this way. And then from here, the result looks something like this. And then we have to perform an integrations by parts on my right hand side expressions. But before that, I'm going to just rewrite the original format first. All right, so there you have it. Okay. Now our last step is to perform integrating by parts. So from here, you're going to we're going to let u equal to x, and then dv dx equal to exponential negative 2x. Right, from here your du dx is a 1, and then the v is negative half e negative 2x. Okay, therefore these equations number 1 here would become, okay, so I'm going to draw a line here so that I can show you the next step here. Alright, so from here onward, I'm interested to obtain the integrating factor. So from here I can rewrite this as x exponential negative 2x from here, from equations number 1. Now that would be the same as uv. So the formula is uv minus v du dx integrating that. So our uv we have negative half x e negative 2x. All right, and then after that we will have our half, and then when you differentiate it, it's a 1, so therefore that will be our form at this point. And then after that we're going to finalize these integrations, so that we can get okay from here itself is 1/4 e negative 2x, and then of course finally we have to end it with a constant there. Therefore, if you want to, oh yeah, I think I forgot my y. Did I forgot my y? Yes, correct. So my y, there's a y here. Okay, I forgot my y. Let me write it down. So therefore, there's a y here, right? And then from here, I have a y. Okay. Now, finally, if you want to write the explicit functions for y, which is a general solution, so the general solutions for these equations will be, we can divide all the equations left hand side, right hand side by x exponential negative 2x. Therefore, I will have negative half for my first one, and then my second one will be 1 over 4x, and then finally I will have my c exponential 2x over x there. And then of course in this case they have already made a restrictions, knowing that the x is greater than 0. That's the reason why we can divide both sides of the equation, and then this will be our final solutions, general solutions to the first order ordinary differential equation, right? So I hope this has been a clear methods to show you you can use the longer versions of using the integrating factor, or you can make use of the result of the integrating factor directly from here. You can use these results directly to solve any first order ordinary differential equations that can be written in this form, dy dx plus fx y equal to gx. All right, I hope that is clear. Until I see you again, stay tuned for the next latest video. Right, don't forget to subscribe and then click the notifications bell so that you can receive the latest video. Right, until I see you again, take care everyone.